I have been summoned. Good evening and welcome everybody. This is Obi-Wan Piz for N Simplex Pachinko. We are going to be doing differential equations tonight. So thank you very much for coming on in. And thank you to enstucky for bringing over your raiding party. As soon as I actually remember which window I need to... There we go. Okay, we are now live on the event stage for anyone who is here. We have enstucky and e to the 2i pi, Zach, with us this evening. And like I said, live now, so whenever you're ready, you can introduce yourself. Oop. I know what I'm doing, I promise.
I'm here. We're good.
I just got in.
Yep, Stucky, I'm sorry about that. I clicked invite because I didn't think that I invited you, and then it moved you back to the audience.
Gotcha.
Whoops.
Yeah, I'm enstucky. I came a week ago and saw a little bit of the Wednesday class. Excited to see where we're going. Oh, there is the link.
And if anyone does not know these wonderful people, we have their... Which window am I in? Come on. Come on, Obi. Compiler ate your homework? Yep, definitely. We have the list of our math chads right here. So we have Dawn does math, Zach at e to the 2i pi, Penn Center, enstucky, Obi, that's myself, Danny Highway, and Dr. Gold at Actual Education, who are our... You know what, that's not everybody anymore. Our community expanded, and I need to add to that. We also have... Right, Discord links. Oh. I can't remember who's under an alias and who isn't on the commands list. Okay. Hello. Okay. So we're going to be taking a look at our differential equations. I'm not doing anything, I promise. Okay, so on Excaladra, we're going to take a look at, let's see, 15, 52. If y'all would please discuss the nature of separable differential equations. And with the link I posted in the differential equations chat, that'll also get you onto Excaladra if you wish to add anything by drawing.
All right. Oops. Am I talking?
Yes.
Cool. Right, so when I think about a separable differential equation, I'm thinking about something that I can write in the form Ooh, that's not writing. That's writing. It's very thick writing, but we'll survive. Not usually my favorite choice of symbols, but so I'm thinking about something that I can write as like the derivative. A first order derivative is equal to some fraction, and the important bits is like one side is all x's, and the other side is all t's. You can flip them if you want. But yeah, in particular, separable always makes me think of first order. I guess always makes me think of ordinary. Just trying to use some of those words that I remember from last week.
So in terms of classification, yeah, generally speaking, we're going to be doing it with ordinary differential equations. In theory, you could have partial differential equations such that this works, but usually they're going to be special cases.
Aye.
I was gonna say, I don't know if I have anything to add to that. I think Stuki did a good job there.
And I suppose, do they need to be linear?
Nah, maybe. Hold on. No.
Why not?
I'm perfectly happy to write x squared up in the numerator.
Right, and it doesn't actually cause any problems in terms of like trying to find an integral of that particular function. And homogeneity.
Homogeneity.
So the shortcut for this is that, sorry, Stuki.
You're good.
If I remember correctly, the shortcut for this is that you have a right-hand side equal to 0. But that you, and that's like the sort of the big thing that we look for. There is a little bit more to it, but no specific solutions, or no particular solutions. Sort of the antithesis of being having a particular solution.
Okay, so if we had, for instance, this setup here, right? What would make it homogeneous then?
So generally that means that you have a function of variables, right? So you have your nth order derivatives, and then you'll have a term that just has the independent variable in it, right? So that's usually what happens.
So I think we said it was n.
I'm not being very precise right now, so
I hit a button.
being pretty informal. But
that's fine.
But yeah, you have a function of, what would you say, t and y, and then you'd have a function of in one term, and then you'd have a function of just t as another term.
So in terms of what we had last time,
Sure.
we had something that looked like m of t dt plus n of x dx is going to be equal to 0.
Sure. Sure.
Yeah. All right, so this is kind of our general form that we were looking at from last time. Modified this time for x and t rather than x and y, but whatever, you get the point. So in this particular case, what would make this homogeneous? In this particular general form.
I think we need n to be 0. M, sorry. That one.
Right. So m of t would need to be equal to 0 in the homogeneous case. What would that do to this whole equation?
I guess it reduces it to like dx dt is 0.
Well, not necessarily dx dt. Oh. Yes,
dx
it would.
by dt, sorry.
Yes, it would.
Yeah,
sorry.
as long as you can divide by n, I guess.
Right. So what we'd really have is like n of x dx is then equal to 0. So the derivative of this particular function would have to be equivalent to 0 just by itself. And yeah, dx dt by itself would just end up being 0 once we move the dt over. So my more general case of this would be that we'd say, okay, this is going to be r dt I'm okay, I promise. So when we look at this, we'd say, okay, well, this could end up being whatever function we needed. We'll do kerning or serifs. So some big N of x would just be equal to 0 or equal to a constant. And that's a pretty boring function in terms of what's going on there.
Yeah.
Yeah, Zach, you were saying about saying goodnight to your kid there. So.
Oh no,
Or
I'm
saying-
good. I've been listening. I'm letting you finish your thought, so I don't want to.
No, I just mean mine
Interrupted
popped her
things.
head in. So she is not 4 months old.
Well, she's not in here, so we're
Yeah,
okay
yeah.
now. But yeah, I had my 4-month-old in here a little while ago, and that could have been interesting to have her on the air.
So I would argue that in this particular case, a homogeneous differential equation would make for a really dull solution. In this case, right, just whatever function it was of x is now going to be a constant. So it could be a homogeneous equation, but most of the time it's not going to be. All right. Any particular questions from chat or from our participants? And if there were any other people who were interested in coming on in, again, anybody who is, kind of a regular on any one of our channels, if we can vouch for you, you're welcome to participate as well. Go ahead and log into Discord, and if we know who you are, we'll get you set up.
Hinting at nobody in particular.
I was gonna say no hints.
So Danny, the classification section is Like, uh, yeah. So classification is not like a particularly useful skill in a vacuum. However, when we're doing this, usually what happens, especially in like partial or nonlinear differential equations, is we're like, hey, if this is a partial first order linear differential equation, it will always be solvable. I can't actually vouch for the validity of that statement, but nonetheless, if it is of this particular class, we can always find an answer for it. And if it's of this particular class, then we need further conditions to determine whether or not we'll always be able to find a solution, or like sometimes be able to find a solution, and what those conditions are. There's some really cool stuff that happens with, again, partial and nonlinear differential equations. Those are the two classes that I took in succession with each other at Johns Hopkins. And those were so like you had a choice of 200 level master's classes to take. And that was my sequence that I decided to take. Everybody had to have a sequence.
I'll add to this a little bit, because when I hear people talk about research in differential equations, there's two cases I think of. One is this nonlinear case, but two, when you talk specifically about a partial differential equation, there are certain classifications that people will research. So you'll often hear the phrases, and I know you haven't talked about this, but you'll hear the phrases hyperbolic, elliptic, and parabolic to describe different classes of partial differential equations that are actually researched. And so having these classifications can be useful to say, okay, I know who I'm talking to in this research field. I know I'm looking in the right area, because there are these words just help me be able to talk conversantly. I know who I'm talking to, in essence. That's one particular.
Anders, yeah,
Anders,
that's a good
yeah,
one.
Anders. Well, that, yeah, it's gonna say like it's useful for stating theorems as well. But I'm thinking in practice, when I've heard people talk, I have a professor I've worked with who does, I believe, elliptic PDE research, and that tells you something about the kinds of partial differential equations he's solving. Or if you say dynamical systems to somebody, I know we haven't talked about that yet either, but like an ordinary differential equation, that tells you something about what the person's studying. So if you're studying linear and nonlinear, usually you'll hear people talk more about nonlinear cases in practice.
Yep.
This has been my experience. I mean, Stuki here, if you want to chime in. I don't know.
Yeah, I have nothing to add.
Yeah, one of my colleagues has a spouse who specializes in partial differential equations. I can't remember what his particular area was, but I also left them a substantial portion of the PDE books that I picked up from the professor.
Mm-hmm.
Okay, looking at number 2, just off to the right there. Looking at this following differential equation, is it separable? And can you figure out, just by kind of analysis, looking at it, whatever, what differential equation, or what equation, what solution it would have come from?
Okay, is this separable? I have to look at that. I believe the answer is yes. I'm doing the math here carefully, but I think I'm just subtracting stuff in my head.
Yeah, I'm convinced.
I'm convinced, yeah, I think it is separable. if we behave as Newton and divide by dx on all sides, right? Like I'm being like Newton, and that's okay.
Which is fair. All right, so what would we get if this is in fact separable?
Let's see here. So you'll
Not
get
always super easy, but nonetheless.
no, it's fine. Dy dx equals 2/3, negative 2/3 rather, x over y, if I'm not mistaken. I'll need the verification on that.
I like that. Yeah.
Like that? Okay. I'm glad you like it too, because I like it. But I was getting nervous. I was like, is my mental math broken today?
So what's going to be on the top versus bottom? What part are you dividing by?
Oh, I mean, I can... like that?
By skipping the subtraction step, you might have made a small error.
By skipping the subtraction step, I might have made a small error, huh?
So yeah, Starig, if you want to come onto the event stage, yes, we can get you in. If you're okay.
Oh, did I... Hold on, is this the reciprocal? Is it the reciprocal? Hold on.
That's what I'm getting.
Doing it. Okay, yeah, I was gonna say I think it's the reciprocal. I think everything just has to be. Dang it! Versus. I knew I had this feeling I was doing it wrong, and I'm like, my feeling was right.
Yeah. So if you're.
Yeah, dang it.
Okay, you could.
You could do it that way. That works.
Yeah, dx/dy is perfectly acceptable. It may not be what you're used to doing, but, you know, whatever, it's fine. Okay, so why is this separable then?
So here it has my preferred form. Right? This, I mean, if we have a derivative on the left-hand side, and then one variable on the right-hand side we have a fraction. One variable exists only in the numerator. The other variable exists only in the denominator.
Okay. So as we had discussed, I think last time, right, we said that this could also be written as our m and n as a ratio of the two. And it doesn't actually matter which one's on top or bottom or whatever, because as long as the eventual point is that we're able to get these exclusively set, so that this is like, no, wrong way. Right, man, I'm having a day. We only just started. Dx over m of x is equal to dy over n of y. Something like this. It doesn't have to look exactly like this, but the point here is that we have variables that are completely separated from each other, hence the name separable, and can be isolated as multiplicative terms. So when it looked like this all the way at the beginning, it kind of looked like, oh no, this is not going to be separable because these variables are all mixed up together.
Right. It
kind of does get some students, especially, very beginners of differential equations, a little either tripped up or nervous that, like, just seeing variables together is automatically disqualification. And that's not true, right? In this particular case, we saw that we do have a nice... that's all right. If you do select and just go around those... Yeah.
Gotcha.
I did the exact same thing last week, too. What was it? Yeah. So if we create this ratio that has specifically these bits in it, so our functions of x on the top and our functions of y down the bottom, that's acceptable to say these are isolatable and by multiplicative terms. Right? It does the exact same thing as all of the other types of forms we've seen. All right. So, if we say that, okay, under some conditions, it might be possible that our separatable differential equations might be able to look like this, where we have multiplicative terms only, and then we can, again, shift stuff around. It's possible that the general form could look like what? I am being intentionally vague, so...
Like growing up m and n into two variable functions?
Right, so these could then look like m of xy dx plus n of xy dy is equal to 0. Again, might be separable if all terms are multiplicative. Within m and n. Would that be fair?
Yeah.
Mm-hmm.
Okay. So we're going to shift gears just slightly, and in this particular case, the second question is not explicitly figuring out, like, oh look, it's separable, let's solve it. But in this case, from what equation originally would we have gotten this as our differential?
So one more time. Could you ask that one more time for my sake? I didn't quite catch all of that.
So given the left-hand side of the equation that we see here, of the differential equation, is there any obvious original equation or solution that would have produced this had we taken its differential derivative?
So my thought here, excuse me, my thought here, I would say it's like e to the, it's going to be some function of e. It doesn't, I mean, it's not super obvious but just by looking at it, but I'd have to, if I integrate, you're going to get a 1/3 natural log, I guess, be 1/3 natural log y, negative 1/2 natural log x, which, gosh, what is that going to be? So it's not, I guess it's not super, like, obvious to me, but...
Okay.
But,
So
like,
what...
I mean, I could do, with some effort, I could figure it out, I think.
So what if we went to this side of the equation and said, what about that? is there anything obvious that this came from? To say like, okay, this is all equivalent to the derivative of something.
Well, so here's something that's interesting. I'm noticing. I mean, it feels like there's a product rule going on here, of sorts. And I'm trying to find it. Like, I'm trying to think of said function, and I happen to have found something. As I went through and solved this formally, and I'm double checking whether that solution will make sense. Yeah, I was gonna say I'm with Anders too. Yeah, it looks like the product rule. I mean, that's sort of the only thing I can think of. But like usually we think of this. Is that what I was trying to figure out what you were asking too? And I think Anders is hitting it too. That if it was some function of two variables whose total derivative is that thing. Yeah, I can sort of start to see that now. Yeah. So what that would be? It would be what would it be? X cubed y squared, wouldn't it? Because the reason for that is you're taking the derivative with respect to x. I see what you're getting at now. Okay, so yeah, you can take the derivative with respect to x of that function and get 3x squared y squared, and then if you take the derivative of y with respect to that function, you're going to get 2x cubed. Yeah, that checks out. Yeah, no, I think I see what Anders is talking about. Now I get you. It took me a second.
Yeah. So where I'm trying to go with it, right, is that we're saying, okay, we do want to take just the total derivative, as you call it, of the original function x cubed times y squared, and that gets us all of these little bits. So it is a total derivative. Okay. So I will call this the general derivative operator, where we're just like saying like, I just want to take all possible derivatives of these things. And for better or for worse, I've decided that over the years, it's just been a lot easier to say, you don't have to worry about this in terms of partial derivatives or whole derivatives, as it were. I just say, let's just take the derivative of x and we get dx. Let's take the derivative of y and we get dy. Now, again, as you said before, some people may be very angry with me about this, but generally it's not going to be the algebraists or the differential equations people. So it's analysis, right? Is that the sticking
Analyst,
point?
Yeah. I think analysis would be the one group who would be angry with you. And history of math says Bishop Berkeley would have a problem with what you've done. He called out Newton. He called out Newton quite heavily. So.
But the idea is just that if you want to take the derivative of x, it's going to be dx. If you want to take the derivative of y, it's going to be dy. You don't have to have a particular, like, with respect to this variable. It's just, again, like, what kind of derivative are you going to take for this? So when we have this product of two numbers, x cubed and y squared, then we could take our generic derivative operator and get the whole left-hand side of the expression, left-hand side of the equation that we saw above. Okay, so the original, normally what we do is we say, okay, this combines this m and n into, like, its combined integral or antiderivative, which we usually label as c of xy as the solutions to this particular differential equation. What about the right-hand side?
could be a constant.
Right, if the right-hand side gets a 0 when we take the derivative overall, then it had to have come from a constant to get there. So again, we're saying like, okay, this is deep C is going to then be, again, this 3x squared y squared dx. I'm just going to keep going down here, sorry. Plus 2x cubed y dy, and that is then equal to d of c, our constant, which is equal to 0. Okay. So, let me just double check what my next question is. Yes, okay. So there is a name for these particular types of differential equations, which come from a single multivariate function whose answers are c is equal to some multivariate function is equal to c, a constant. I don't know if you or can recall what name I'm going for here, but
this is the exact ones, right?
yeah. So these are called exact equations. And then we want to talk about what properties do exact equations have, and or what do they look like. Right now, we at least know that typically it's going to be labeled as c of xy, and then generally that's going to be equal to the constant c over on the right-hand side. Are there any particular special properties that this thing might have?
Yes, we should call them Zach's equations, Anders says.
Probably have to fight somebody for it, but
I mean, it's our little thing, right? It's our class, so we can name whatever we want.
yeah.
The way I see it.
St. Just Germany. Good evening and welcome. My name's Obi-Wan Piz. This is N Simplex Pachinko. We are doing differential equations class tonight. So we have on the line Zach from e to the 2i pi and E.N. Stuckey.
I'm gonna say I recognize St. Just Germany. It's been on my stream a few times.
That's not what I wanted to do. Okay, there we go. Okay. So, do we have any particular properties that exact equations might have? Or any way to link it to what we did before?
Well, I mean, if you can write it as a, I mean, if you can write this as in terms of partial derivatives, I wonder.
Mm-hmm.
Right?
Like
so,
what?
like, if we might be able to solve this, like, in the way we did before. The nice thing was there was a function that, so going back, if we can go back over to that other example, 3x squared and so on. That there was a function that this x cubed y squared that the derivatives came from, right? So there's this sense in which we took the derivative with respect to thing, we took the derivative with respect to y of this thing, and got a differential equation out of it. If there's a way we could find that common function systematically, then I think this could be helpful. Because then we'd know that systematic, like the function this came from, is a constant.
So for
I
an
don't know if
equation,
that's which.
sure. For an equation
That
that
works
is
for you.
exact, what's m?
What's m?
Yeah.
Well, the way we've written it, it's a derivative with respect to x, yes? Because we've got a... Sorry, we good? It's a derivative with respect to x, yes? Of that function we found, because we have a dx term here.
Right, so the partial derivative of psi with respect to x is m that we had from before.
Mm-hmm.
And also?
With respect to y is m.
Okay. And then what?
Well, I guess you could write the whole thing as a psi x dx plus psi y dy equals 0. That would be the,
Right.
you know, you could substitute, right?
So it's going to be separable if we can rewrite this as psi sub x, or sub, but partial derivative of psi with respect to x dx plus partial derivative of psi with respect to y dy is equal to 0. And again, this is exactly equivalent to what we just saw over there. Okay, and then the next question, or if you can anticipate it, is there a quicker way to then be able to see whether or not any particular differential equation is exact?
So, sorry, go ahead, Stuki.
Just let me know if this was your plan. So we have. So if this psi exists, we know by Clero that those things have to be equal.
Yep.
And so, being an algebraist, I'm going to throw parentheses here. So I don't do
That's fair.
anything except for manipulate parentheses.
Bingo. So as we're looking at this, we say, okay, if we go back to our previous notation where we had just like an m and an n that were attached to these dx's and dy's, if we can show that the partial with respect to m, which was in terms of dx, or multiplied to dx, and then we find the partial of n with respect to x, where that had already been taken with respect to y from like our psi, our solution, then we can show that if these things are equal, this is a perfect exact equation as is. We don't have to touch a thing. All right, so then that's going to tell us that this is a differential equation that can be solved almost entirely by just saying, hey, this is a product rule. Let's figure out what it is. Now, in many cases, it's not going to be obvious what it is specifically, but that's okay. We have other methods. So So multiple different ways exist of like how to organize this and show what it is that we have to do, but I found probably the easiest is just to say, okay, we've got this equation that we're looking for, psi. We know that psi with respect to x, partial derivative of psi with respect to x is going to be our m. And we know partial derivative of psi with respect to y is n. So we can just go from here and say, what would happen if we took those particular integrals going back? So can we take the integral of m with respect to x and n with respect to y, and we should get the same thing. Any arguments?
Right. Well, and I think Danny's question's a good one. What when m and y equals nx, what does that tell us? What that tells us, and you can add to this, I think you might need to, depending on what I say here, if I speak blasphemy or whatever. What that tells us is that the second derivatives are equal, and this is a notion of continuity that comes from multivariable calculus. That the mixed partials are equal, that means that there's going to be some kind of potential function. That's sometimes what it's called, which is that the thing that equals c that we can solve for psi. We'll be able to do that if we have this my equals nx, which is basically saying that the partial with respect to x and y of one function is equal to the partial with respect to y and x of the other. Well, so there is. Yeah, this is related to conservative functions. Yes, Anders. Yes.
Mm-hmm. I'm not sure that I've ever heard that term before, but...
Well, so it's... I've heard it called potential functions, but I think the principle's the same.
Okay. So given that information, right, we can go back to our previous example and kind of prove that psi of xy is going to be x cubed times, y squared. I thought I misspoke there for a second. And show that this does work the way we expect it to. And I'm not just saying like, hey, we're going to have to guess what this product rule is. Like, no, now we're going to get our algorithm in order to find analytically what these solutions are going to be. Somebody want to do this one, or?
Sorry, do.
So we know that psi partial of psi with respect to x was from before. Well, okay. I guess we can't say it's necessarily psi yet because we haven't proven that it's exact. But our m was equal to 3x squared y squared. And our n is equal to 2x cubed y. Yep. So first of all, we want to show that this is an exact function. Nope. That this is an exact differential equation. That's better. And then show how to find the solution psi from m and n.
looks like that's going to be 6x squared y. And x, take the derivative of x cubed, 6x squared y.
Woo! Right, so since these things are equal, we can say, this is an exact equation. So our differential equation is an exact one, which means that our solution will be some overarching multivariate function psi of xy equal to constant c. So now to go back and say, okay, how do we get what that equation is going to be?
So this is where we're going to have to integrate m and n.
Mm-hmm.
And since we have something in dx, we'd want to integrate m with respect to x, or n with respect to y, and then solve for some constant function that comes out of this, because this is a multivariable function.
Right, so in this particular case, when we're taking the integral, everybody's like, oh, remember that plus c at the end that you put? Well, because this is a multivariate integral that we're taking, we have to specify that when we're taking the integral, this is going to be, again, if we're integrating m with respect to x, then we are going to be just doing a kind of standard integral in terms of x, but then when we get the solution, as Zach said, this is super, super important. Our constant is no longer a constant just number, or at least not necessarily. It could be any sort of constant with respect to x. And in a multivariate function, x comma y, that means that y is constant with respect to x. And so if we take the integral of m with respect to x, we're going to get a constant function, let's call it f of y, tacked onto the end of our integral. Does the result from an integral have a special word? Integrand?
Is that the result of an integral?
Yeah.
The result.
Cool.
I mean, I don't know any special words. I know it's the antiderivative. I mean,
yeah.
You could call it that, but
that's fair. I'm just thinking, like, integrand is the interior portion of the integral, so.
Oh, there's the integrator. If that's the dx part, that's a fun part. That's a fun word I learned.
I just always call it the differential.
Yeah. By the way, I'm gonna have to duck out here. I have a meeting at 3:00 that got changed, and I didn't expect this. So I will be here on Wednesday, but I'll have to duck out for a little bit. Might be back.
Okay. Thank you, Zach.
Good luck.
Cool. Yeah, thank you.
And it appears that Star Egg is also interested in coming on, maybe? Or if you're just in the audience, apologies.
Yeah, I think Egg mentioned earlier they don't have voice chat, but if you wanted to come on to start writing stuff down in in the Excalibur, I'm sure we could make that work.
Yep, gotcha. So we have this link here if you are interested in writing. All right, so Stuki, what are we going to get for our integrals of m and n?
let's do it. So this one, right? That's gonna be square dx. That sure looks like an x cubed y plus c with respect to x, which is, get rid of that annoying error. So it's a constant with respect to x, which means that it's some function of y.
All right, close.
Darn, there should be a squared, because I forgot to copy that down.
Okay, and then what do we get for integral of n?
I see what happens here. Just gonna be the same plus constant with respect to y, which means some function of x. And these are equal. I mean, I guess we know they're equal because we already did the checkup above.
Yep.
And the only way that you can have a function of y that's equal to a function of x is if they are constant.
Right, and since we're going to take them together and say phi, psi, not phi, psi of xy is going to be equal to our x cubed y squared, and we had this set equal to c as like some constant, just constant. I'm sorry, Ag. Yep, and let me know if you do want to catch up outside of class. We can have a chat or something like that. Okay, so you're absolutely right. The only way that we could potentially have c of y be equal to d of x is if we had some other constant like this c1, which was added to x cubed plus y squared. Nope, x cubed times y squared. So we could add c1 to it. But again, we've talked about this before. This is just the equivalent of moving that over and making it a different constant. So we don't need to write any of that stuff. And we could just say, all right, look, this is just going to be equal to a constant, generically called c. And our psi function is going to get us this thing. Alrighty. Any questions in chat or... Oh, yep, see you, Danny. I agree, Fembox. Okay. So for this, right, we're just going to have our psi equals x cubed y squared equals some constant c. Interestingly enough, right, if we go over to Desmos and plug this in... Nope, cubed. Right, we're going to get an answer if c equals 1 that looks like this. If c equals 2, it's going to look like this. C3, 4, 5, 6, 7, 8, 9, 10, 50, 500. And it's going to be just ever so slightly different variations on the theme. We might be able to even go negative. Yeah, cool. So we've got all of these different constants that can be plugged in for C, and again, we could just that's not going to be helpful. So negative 50 to 50, we'll just do that. So if we animate this, right? These are all the possible different solutions that Desmos can plot with a step variation of 0.05, I think. And if we were to actually, I don't know how to do it actually, but if we were to show all of these at once, right, we could put in a few. I think I'd have to manually insert several. That'd be kind of a pain. But if we could put in multiple different values for this and show like what our solutions would be, that would be able to show us a sort of map of what kinds of solutions we would get for what kinds of values of C. So for instance, again, we got something that looked like this for one particular value, like this for a different particular value, right? Some various intermediaries, things like that. So this one's kind of boring. We'll see some more interesting results later, but we can end up getting results that look much more interesting. Is there anybody out there who has seen something like this before? And I think that's actually my next question anyway. Really? Come on now. Yeah, so Anders, yes, it is a family of hyperbola for this particular solution, right? And like I said, this one's kind of boring, but Femvox, bingo. If you have ever seen a contour map before, this is it. This is how we are going to look at each one of these individual lines are called nullclines. They are essentially like, what value of C are we looking for each of these? If you're looking at a contour map, so like actually going online and finding like a USGS, the Geological Survey maps, things like that, you can go out there and find contour maps which show like your area and all of the individual altitudes for those particular things. Popped out one of the exercises. Yep. And Starg, yeah, if what you're saying is MATLAB. Oh, machine learning. Okay. Yep. So gradient descent, or like the method of steepest descent. You can get that kind of stuff showing up in machine learning and a whole bunch of other stuff. So the learning function that you're going through, everybody's kind of seen like the two-dimensional version of this, where you're looking at this and you're saying like, you know, you've got this machine that's learning how to do various things. And like when it's doing text recognition, for example, right, it gets enough information to be able to fall into this like local minimum right in here, but it's not able to go any further. Right, let's say that there's a, you know, actual absolute minimum over on this side. A computer would not be able to find the absolute minimum if it gets trapped into a local minimum. So it could, for instance, recognize all of my C's as E's for some reason, if there's enough noise or something like that. And in that particular case, it would be really annoying. But with nullclines, we're basically showing like what's happening at each of the individual steps for C. So if we're doing a topographical map, you're doing like every 100 feet or every 20 feet or something like that, change in elevation, you're putting a new nullcline in. Okay. Ads are about to start, so yes, we can do some exercises after main class. I'm going to hit a 3 minute so that we get the rest of the hour clear, and everybody get up, stretch, cycle your water, do all that stuff. So, see you back in 3, and Stucky, if you have any questions, let me know. I think we're good, though. So
I'm doing good.
All right.
See you
We'll be
soon.
back in 3 minutes.
All right, mine are finishing up over here.
Yep, I got mine out. All right.
Cool.
I decided to redeem AR. So we're going to do a quick learn a word in main lingo. So those of you who have not been here before, I grew up in New England, on pretty much on the border of Maine and New Hampshire, and I grew up listening to a particular sort of like a radio series, but it was really live performance art at our local town fair, which was called Bert and I, B-E-R-T, Bert and I, but said with a down east Maine accent. This particular accent comes from, well, I mean, obviously, it's called down east, but Maine's coast kind of goes like this, and those of you who have played Fallout 4 or the associated DLC, there's a place called Bar Harbor, or Bahaba, which is like most of the way up. It's probably about 4 hours by car north of the border along the coast. And John Gould wrote a book that is called Maine Lingo, A Wicked Good Guide to Yankee Vernacular. So I listened to Bert and I for many, many years, and I thought it would be kind of funny to spread the word a little bit that it exists. Marshall Dodge and Robert Bryan did this study. They were roommates at Yale and decided that they were going to study the storytelling methods of the Down East Maine fishermen especially, but townspeople in general, because they had a very particular way of talking. So I have opened two, and the first one that I came to is called John R. Braden. So John R. Braden is a sure thing, a winner. John R. Braden was an incredible harness racing horse in post-World War I days who held and broke most records. He had his personal bank account and was once honored guest at a testimonial banquet in Presque Island. He is buried and memorialized at Northern Maine Fairgrounds. Hence, to have anything virgin on a John R. Braden is said to be well fixed. A popular song all Mainers sang in the 1920s had this couplet: John R. Braden, you're a winner, just as sure as I'm a sinner. And Anders, thank you for the hydrate. Thank you, Story. Thank you. I have also done a very small number, like one, of the Bert and I stories as performance art last year at some point when I was still in Maryland. So I might decide to do that at some point later once I actually, like, you know, gain confidence in it. We'll see how things go. Stuki, thank you for bearing with me.
Y'all good?
Too convoluted. I'm sorry, Anders. So it's a very particular storytelling style, and I love it. I actually created a D&D character whose entire, like, the entire premise of him is that he knows the Down East Maine storytelling style, but it comes from Frost Giants. So, like, he hung out with the Frost Giants and they taught him this thing. So my D&D table was rolling with laughter with some of these ridiculous things and stories that I come up with. But as a bard, he inspired people. Okay. So now we get to the next section, which is we're going to try out a couple of differential equations and try to solve these particular differential equations using the same method that we looked at from before. I think I got those. Yes. Okay, the parentheses are correct. If slightly distracting.
All right. What is the plan? We're gonna do a same format here.
Absolutely.
Okay. Egg, I see you wandering around. Do you want to start writing out part A? I'm assuming that's Egg. Could be anyone.
I imagine. Don't feel confident. That's okay. Yep.
Fair enough. Right. Let me pick a color. Green. Okay. So, is it exact? Well, I guess there's a question before that, because this is not written in our favorite format. So, format. We've got, maybe, oh, canvas is big. Let's call that dy over dx. Multiply through by dx to get 6xy plus 3. 3x squared plus 7 dy is equal to 0 times dx. Love it. Cool. So this is m. Is that right? Which one is which? M dx. I think that is.
Almost correct.
Oh no, did I typo?
Yeah, just a small one. N. 3x squared.
M dx? N dy?
N dy.
N dy. I think we agree. Wait. Yes, okay.
Right here.
Yeah.
Sorry.
Yeah, all good. Oh, minus. Ah. Boop. Okay. Is it exact? Well, m sub y is equal to 6x. And sub x is equal to, looks good, 3 times 2x, and the minus 7 goes away. And to solve, we can integrate some m's with respect to x. And that looks like 6xy plus 3 dx, which is, I'll go 3x squared y plus 3x plus c. Constant with respect to x, which means a function with respect to y. Double checking that. I think I'm happy. do it again. 3x squared minus 7 dy, which is going to be 3x squared y. I like that. Minus 7y plus d, which is a constant with respect to y, so a function with respect to x. And supposedly these things are equal. So that means that 3x plus c y minus 7y, oops, 7y plus dx is equal to some constant.
Sort of.
No, I'm pretty sure that's right.
What did you do between the two equations?
So these two things have to be equal to each other.
True.
So that's... excuse me, no, sorry, no, not that they have to be equal to each other. No, they do have, they do, sorry. Yeah, so I guess I could just set that to be 0. I could absorb that constant into the 2.
So there's a little bit of a problem.
Okay. Which is probably a sign issue.
Yep.
That's fine. I'd rather have it this way anyway.
Yeah, so if we have a... Oh. So if you're going to stick the equality sign in there, right? Yeah.
Then the minus.
That should be a minus 7y and a plus d of x.
Yeah. Okay. So feels like cy should be negative 7y, dx should be 3x. There's a fudge factor of a constant. So overall, plus 3x minus 7y plus.
Yep. And typically at this point, we usually just say that's going to be equal to c. So that it's just, that's telling us what the nullclines are, that all of our individual c values can be constant, or the values of this whole function as a whole are going to be constant. It's not like it really matters, right? Because it could just be plus c and then equal to 0. But typically you're going to see all of your c stuff with the variables over on the left, and then your constant over on the right-hand side of the equation. Just makes things a little bit easier rather than making it equal to 0.
Yeah.
Alrighty. So that's going to be part A, and for part B.
Okay, cool. Part B. doing that over on the right. So here formatting is good. So this is M, this is N.
Fembox, I think I learned it that way too. So Fembox says, I always like doing these problems with a kind of tree diagram.
Interesting.
So yeah, I'm pretty sure I learned it that way, where it was like you basically make a little square somewhere and say like, this is your m of x, this is your, or m sub x, this is your n sub y, and then you want to again show that their other partial derivatives are going to then be the same thing to make them exact, and then yeah, right, yep. You make a tree diagram going down that says on the left hand side we're going to do this, on the right hand side we're going to do that. Yep. So I think I did learn that the same way.
Just checking, but I think that is no, never mind. That is not right. N is cosine x, so derivative is sine x. Yay.
Woo. I was gonna panic there for a second. Oh no, wait.
Cool. Zoom out. We'll see if this affects the quality of the handwriting. Okay, so integral of m dx is equal to integral of some hot nonsense.
That's fair.
Sine x plus y, sine x. Two cosine x dx. Okay, I think we can do the rest. Zoomed in. Okay, where is that drawing tool? There it is. Okay, and this is equal to cosine x plus, wait, integral of sine is minus cosine. Integral of sine is minus cosine. And integral of cosine is positive sine. And y. Integral of cosine x dx. Get fancy with the brackets, apparently. And this is positive sine.
Yep, always trips me up too.
Okay. So, oh, there's a lot of terms. Okay. Cool. But that, okay. Let's see here.
Oops. That wasn't what I wanted.
Have sine x plus c is equal to minus cos minus y sine, or cos minus 2 sine is a little concerning.
Next
So,
question, did I forget something in my
no, I
original question?
integrated with respect to x instead of y.
Oh,
That's
okay.
what happened.
There we go.
um, so that's y cosine x plus dx. And so that's going to change u to y cosine x. And do some matching, fun matching games. We get...
Oh.
Oop.
Nope. Okay. Your y sine of x started as negative, actually. So would it change to positive?
Gotcha.
That makes things much better.
It does make things much better. We knew it had to work out.
Yeah, and this is also for anybody else out there who might be doing this in the future, right? This is something that's going to be part and parcel to like all of the differential equations that you do, particularly at this level. You're going to come across exact equations, and it's going to be much nicer to like double check to be like, oh, look, all the stuff that has mixed variables went away. Perfect, because your c should only be a function of y, and your d should only be a function of x, or however you stated them.
Minus.
So that's absolutely perfect, yeah. Whew. All right. Yep. And then put whatever you feel like as your variable. Okay, so if we go over to Desmos and try it here, this is going to be obviously a bit different. We get a negative cosine of x minus
Both of these look like real functions, which is cool.
Plus, until we get to y times cosine of x, which really messes with this thing. All right, is equal to c. Add a slider for c.
Oh, I don't think so. It's not a cosine of y.
I guess. Right, we get these things which sort of look like tangent functions with c equals 1. And then as we alter our values again, we start seeing that these pull apart almost like secant or cosecant functions. So it has these very interesting behaviors. And again, this is showing us all the different nullclines which exist for this particular function. So you could show this as a topographical map. It'd be kind of awkward because some of these things would overlap a bit, but... would they actually? No, they don't. Never mind, we're good. Alrighty. Does anyone have any particular questions at this time? Yep, Anders and Femvox, thank you very much. Yep. And I agree, very pretty. It would be a bit better if I had set this up like on MATLAB or something to actually accept some inputs and show us what the nullclines were as like a topographical map. But yeah, it's a little challenging, but it's not like super hard. If anyone is interested in trying this out, there is a series of M files that you can upload to MATLAB, or if you go to Octave, there is an Octave online. There we go. Octave Online, octave-online.net, which, oh no, get rid of the ad. Yeah, there we go. Let me post that in chat here. So octave-online.net. That would be good. Anders? Is everything all right? Did I turned on my microphone? That's good. Uh-oh. What's going on? Too fast? Better? Okay. Oh no. Are we getting a GIF? Alright, now I think that was that the last one? Yeah, yeah. So that was my last screenshot. We have one more section to get through. And what I'd like to do, this is normally done kind of like on its own, but I had a really good experience with one of my differential equations classes doing this, and you all are on top of things, so you know. So a little bit to the right here. We're going to have this one here, so y plus, parentheses, 2x minus y e to the y times y prime is going to be equal to 0. So first of all, let's classify this.
Ooh. Okay. Well, it's pretty nonlinear.
Nonlinear.
Yep.
All right, and for anybody who wasn't here for the beginning of that, what tipped you off to it being nonlinear?
The e to the y. That feels real bad.
And in fact, even if the e to the y weren't there.
Right, we can y times something times y-ish. Oh, y times y derivative.
Yeah, there we go. Right, so we get y times y prime, which in itself is nonlinear enough to count. Right, so y times y prime, y e to the y times y prime, like all that stuff is nonlinear differential equations. So we're not going to be able to solve this strictly analytically necessarily. Certainly not by using just standard linear methods, but we'll see how this works out. So, what else?
Doesn't look really separable either. If I subtract y from both sides, then yeah.
Yep. I will say that this isn't typically in like the classification, but it is definitely useful. So just thinking to yourself, is this thing separable or not? Yep. In this case, yeah, not so much.
Read. Fembox says first order. Ordinary, nonlinear, homogeneous. That looks homogeneous. Yeah, everything's either multiplied by a y or a y prime.
Yep. So we don't have any x function terms just by itself. Yeah,
Right.
everything is either multiplied to a y or a y prime. In this case, right, the y prime and the x are multiplied together. Okay. So based on stuff we've done today, what else do we want to try with this?
I guess we could still ask if it's exact.
Definitely, right? So no matter how complicated some of these differential equations get, you could try to say like, okay, look, this is an ordinary first order differential equation. Is it exact, right? We could separate this out as a, y prime is equal to negative y divided by this nasty thing. Right?
Mm-hmm.
Just get y prime by itself and say like, well, we got all this stuff, so like it's possible, in theory, that we might be able to have an exact equation. So let's just see if that's the case. Go for it.
Oops, where am I?
Uh-oh.
There I am. Okay. Sure. Okay, so, I'm gonna multiply through by dx. And I'm gonna zoom in.
Hey, Super Brain.
Right,
yes,
that's
so,
fine.
welcome to Differential Equations class. You've been in a long time and have only really seen me do math in here, yeah. So, enstucky is one of our other math streamer friends, and they are a Stucky, how would you classify yourself? Research mathematician or?
We were just talking about this on stream today. I am a credentialed hobbyist.
You were rubbish at ODEs. Well, perfect. So we're going to be doing ODEs every Monday and Wednesday night, BST, for as long as it takes. In theory, we're going to be ending probably end of August to beginning of September, depending on how fast everything goes, which optional modules we add in, because there will be some optional ones that I add in. Normally, I'm doing this stuff, I think this is the 4th class or something like that in my notes. Maybe. 1, 2, 3, 4, 5. Yeah, this is like the 5th class in my notes. No, even further. Oh man. But, we didn't have to do all of the administrative stuff at the beginning, like, hey, here's how to sign on to Canvas. And all that nonsense. So, and we've got a class of, so far, our participants have all been professional mathematicians or teachers who took ordinary differential equations like many years ago. So it tends to go a little bit faster when we have people who have done it before. But we do try and get a conversation going about what's going on and different ways in which we can talk about the subject at hand. We were doing real analysis over on Zach's channel. That's e to the 2I pi. Let me drop both of you in here again. And here's Stucky's channel. So please do check them out. They're really awesome people. All right, Stucky, what'd you find?
I think one of us has made a typo. Because
Why?
I think that you want me to keep going, but
No, I was just talking too long.
No.
What is your conclusion?
My conclusion, not exact.
Yeah.
Close.
So because we have here our partial of m with respect to y and our partial of n with respect to x are not the same thing. It doesn't even matter like what is there or isn't. It just, they're not the same. So this is not going to be an exact equation. We are not going to be able to solve it the same way we did before. However, I'm going to contend that there is a way to make this an exact equation. And as you said, Stucky, this is real close. So especially when they are close, when they might be like pseudo-related to each other, we might be able to find a way to make that happen. And I'm going to suggest that we're going to...
like x is equal to z plus y.
We're going to say, let there exist some function, mu, which is going to be a function of both x and y.
Yeah.
Such that mu m dx plus mu n dy equals 0 is exact. So given this, might we be able to figure out now how to show that these are exact, or in what way could they be exact? So we're trying to first find a function mu that's going to make our original differential equation exact. So in general, and I know you definitely have the chops for this, in general, could you repeat the exactness test on what we have here?
For sure.
I'm going to slightly apologize in advance. It's not actually that bad.
Okay, so we get mu m y. That's gonna be mu. Oops. Plus mu y m mu. Oops. Let's do a little rotation.
Where'd your m go on the first one?
My is 1.
Is it? Oh, okay. In
yeah.
this particular case, yes.
Yeah.
That's fair.
Okay. So this is plus. There's too many symbols hanging down. I need to. Too many. Times 2x minus y e to the y.
Okay. So if we were to do it just in general, I have the answer here, so I won't make you do it again. But this is going to yield mu sub y m. The page is getting too big, so now it's like skipping occasionally. Plus mu m sub y is equal to mu sub x n plus mu n sub x. So the new question is whether we do it in general like this or with the particular values that we had up above. Does this make it any easier to solve for our original differential equation, or in fact now to solve for mu?
Oh, double wrong direction. Okay, we're back. So what we now have is another first order equation, but not one that I like.
Mm-hmm.
Yeah, I'm not so convinced.
Right, so what I just wrote down below is that now, looking at this, solving just for mu to try to figure out what this intermediate function is going to be is now possibly harder than the original differential equation. So this didn't seem to help anything. I do say seem. So what we're going to do is instead contend that, okay, we can still make this work and make it easier. Let mu just be a function of x.
That's exciting. Okay.
So now try the exactness test on this one.
Okay, so I'm just gonna throw some green in there. So that's gonna kill this guy. Bigger green. And nothing else changes. But we're gonna get so still these two things are hopefully equal to each other, and so we're gonna get mu, negative mu is equal to, so mu is equal to negative, or I guess I can now just write mu prime times 2x minus cy.
Okay. What might you notice about this?
So that is probably separable, right?
At the very least, it is separable in what?
In mu and x.
Right. So this is going to be separable in mu. So we don't necessarily care about like all the other random stuff that's going on, but really what we're going to care about is we now have a differential equation in mu that is separable in mu. So I will, again, just pop over on the side and say, like, in general, we're going to have, this is mu m sub y equal to mu sub x n plus mu n sub x. So again, if we're trying to separate our variables, we end up with a this is fine. Mu sub x n is equal to mu times the quantity m sub y minus n sub x. And then this is going to be mu sub x over mu is equal to m sub y minus n sub y x over n. So again, this is separable. It may not be 100% perfect, but it at least is going to tell us, like, there's a possible solution for this. Do you want to pick this one up from here?
Sure. Not really. The
That's
answer.
fair.
Okay, so this is that sure looks like an exponential. Cause I'm gonna have okay. I have 1 over dx over 2x minus y equals y equals y. And then we're gonna have, let's keep the minus sign over there as well. Over mu. I see. I guess. Yeah. I can't stop you from just doing.
What's up?
Oh, sorry. You're writing down something different than I thought you were writing down.
Yeah. Sorry. I was doing.
No problem.
Yeah, I was doing the other one. We'll just go like that. So I'm going to mute myself to you, I think, and explain how to solve this on my side, just to stream.
Okay.
If that's all right.
Sure.
Then we'll come back together in like 2 minutes.
Sounds good.
All right. Okay. So the way that we're going to look at this is we're saying we have a separable differential equation. We're looking at trying to solve for mu. And so what mu. And what we have now is we have our mu's separated from the n's and m's. Yes, they are themselves functions of both x and y. That's okay. So what we're going to do is we're going to say, if we were to take the integral of both sides of this thing as it is right now, we'd be taking the integral with respect to y on both sides. Over on the left, we have mu sub y over mu. In other words, like, essentially dy over y, a function like that. So this is going to be the natural log of mu. And then that's going to be equal to our integral, which we have no idea what this is going to be. N sub x minus m sub y all over m dy. So then mu is going to be equal to e raised to that same integral. N sub x minus m sub y all over m dy. So in this particular case, we could use this as our function mu, which is a function of y alone. So this is an option. It doesn't have to be done this way. And we could decide, like, which way we want this to go, right? Do we want it to be a function of x? Do we want it to be a function of y? It won't necessarily matter. Both of them should end up getting you the same thing. The question is, which way is going to be easier in terms of being able to find functions, n sub x, m sub y, divide by m, and then take that integral on top of an e function. So it oftentimes takes just a little bit of work in order to say, you know what, I would really not like to take that integral. All right, we're going to come back together here. All right, Stooky, how we doing? How's it going?
Not great.
Okay, what's up?
Not great. Try to finish this out. This oh, never mind. Okay, I got frightened. That's all. Okay, so this is a I can't do that mentally. Continues to not be the correct thing. Okay, so this is gonna be some hot nonsense. I want to put a 2 right there, which means that I want a 1/2 to come out front. So that's going to be 1/2. See. Oops, plus d. X, I guess, and y, just a constant with respect to mu. And then, right, so what we called C before, which I guess we still need a funky name for. Okay, so something like this is true. I think literally this is true. Because we can take c of mu to be the log, and we can take d of xy to be the other log, and life is good. Okay.
Okay, so then we're trying to solve for mu.
Okay. Right, so this is k mu is equal to let's bring that 1/2 inside of here. Exponentiate everything, so it's a different constant now, times e to the 2x minus e to the y. With to the 1/2. And do we have sign concerns? The C is going to take care of those absolute values. I guess we might need the other absolute values, but not in a particularly bad way.
Yeah, so it's kind of gross.
Yeah.
So the way that we had looked at it on the other side, again, was our just in general, what is this going to look like? So if we had taken the integral of our generic stuff up top, we do end up with exactly the same as what you had. This is our natural log of mu as a function of x. It's going to be equal to, yeah, I guess we technically need those, but eventually what happens is this works out in the end because we're using the e, so
yeah,
happens to work out.
Has figured out what the mystery is. I didn't kill the log, improperly kill the logarithm.
Right, so we get this thing, raise e to both sides, i.e. make them, come on now, the exponents, and we get e raised to integral m sub y minus n sub x all over n dx. Okay, so I had told chat that basically that's what we're looking for when we get to this stage, is which of these two integrals is going to be nicer to be able to figure out. So the way we'd had it before, you said m sub y was 1, right?
M sub y is 1, yeah.
So our mu of x, which is what you had here, should be e to the integral of 1 minus 2 for n sub x.
Right.
Over n.
N.
The big thing, right?
Yeah.
What was that? 2x minus y e to the y dx. And again, you were able to solve that part well enough. And I'm going to just go like that, because, yeah, you got it. And then mu of y, if we decided to go the other way, would be e to the, here we get 2 minus 1, it's just flipped around. And then m was, what?
Y.
Goodness. Alright, this is just y, dy. So here, which integral do you want to take? It doesn't even look necessarily that bad in terms of like taking the integral with respect to x. But at the same time, like, yeah, this one's way nicer. So this is the integral of just 1 over y dy, or dy over y, which is e to the natural log of y, which is just y. So even if like the integral isn't that bad, then just looking at the integration factor, I just gave that away. Looking at the value that we found for mu of y is just so much simpler than mu of x.
Yeah.
So my suggestion in this particular case is that we take mu of y equal to y and then multiply that. There we go. Multiply that to all terms and try to solve that differential equation. Okay, so if we go back to the beginning, this was going to be mu times y dx plus mu times 2x minus y e to the y dy equals 0. And then again, we're just replacing all of our mu's. Come on. With just y. Okay. And then in doing that, we're going to look at this and say, Okay, this one's y squared dx plus, this is now 2xy minus y squared e to the y dy is equal to 0. And then we want to know, is this exact? Again, just to double check to make sure that we got all of our individual terms right and all that. So we're going to take the derivative with respect to y of our first term, and we get 2y. And we take the derivative with respect to x of our second term. Our y squared e to the y just becomes 0. And then 2xy just becomes 2y. Woo!
Cool.
Yeah, sorry that this is going a little bit into my plane territory, but, you know, we're getting toward the, well, no, we're over time, so. Okay, so at this point we say, cool, this is exact. We're going to take y squared dx and integrate it. We're going to say that this needs to be the same as 2xy minus, come on, minus y squared e to the y dy, and integrate it. And again, contend that these should be the same thing when we get to the end. So on the left, we end up with xy squared. On the right, the first term is also going to be xy squared.
Agreed.
Oops, sorry. Except that one little bit that I totally forgot. Plus some function of y alone. Okay. So on the right-hand side is going to be xy squared. And then minus, now we've got to take this integral here, which is pretty gross, but how do we solve this one?
Integration by parts?
Yep.
Twice.
So we need to do integration by parts on this thing. Our y squared is going to be the term that keeps winding down. And so that's going to be our u. U prime is going to be equal to 2y dy. V prime is therefore going to be e to the y, and therefore dy. And therefore v is just going to be e to the y. Okay, so we get a uv, y squared e to the y, minus integral of v du is 2y e to the y dy, which again, we got to use integration by parts a second time. Also, we can just tack on a g of x at the end, because we know that this is going to eventually happen, right? A function that is of x solely. Okay, in this case, again, same deal. U is going to be equal to, we could do this however we want, but I'm going to pop the 2 out here. So u prime is going to be equal to dy. V prime is going to be equal to e to the y dy. And therefore v is going to be equal to e to the y. So then we get x squared, nope, xy squared minus y squared e to the y plus 2 times the quantity, and this is where we do our integration by parts here again. So uv is going to be y e to the y minus integral of v du is e to the y dy plus g of x solely is equal to our xy squared plus f of y. So we're going to contend that, again, f of y is equal to all of this stuff. And that these are gone. So therefore g of x is going to be equal to 0. Okay. So this means that c of x comma y is going to be equal to, we had x, y squared, plus all that stuff that just had y. So a negative y squared e to the y, plus 2y e to the y, minus 2e to the y dy, plus 0 is equal to c. Some constant. Alright. What do y'all think? Oops.
Okay.
Oh, did I put too much stuff in?
Yeah.
Thank you. And in my notes, I forgot to carry the 2. Cool. Okay. So then that is going to... And again, this is where we start getting the cool pictures. Just generally speaking. xy squared minus y squared
That's what looks tricky.
e to the y.
Although
That's 2y.
it's a function, it's a nice function of x. Kind of a weird function of x, but
2e to the y equals c. Right. So here, if we allow this to play, again, we get kind of our border condition right around when c is equal to negative 2, 3, somewhere in there.
in E perhaps.
I wonder. It would make
Yeah,
complete
yeah.
sense, right? So let's pause
It
this.
feels
Let's
right.
actually say, let's actually just say, what is negative e? Nope. Ah, so close. Yeah, it's like
Mm.
2.4321. 05?
Oh, it's less
I
than
was just,
2.
is it just 2? It is just 2, I think, when it has no asymptote. It's just exactly on
Oh, okay.
undefined comma 0. Yep. So our x value is not defined there. Interesting. Okay. We could probably work out exactly why that is later. But at any rate, so this is actually something that's super important. That was weird. Music just went away. So this is actually something that's super important. When we start looking at our differential equations in general, it didn't have to just be exact. And in fact, when we go back to the first part here where I said, like, hey, let's look at this particular function, right? Y plus 2x minus y e to the y times y prime is equal to 0. We were classifying this as first order nonlinear homogeneous, or ordinary, but this particular method will work for all ordinary first order linear differential equations. So no matter what we have in here, if we ended up with something that, if we ended up starting with down at the bottom, some function p of x times y prime plus q of x times y equal to r of x. Without keeping you much longer, sorry. what we can look at is say, hey, if we wanted to do this as above and say, you know what, this may not be an exact equation, but I bet we can make it an exact equation. We can look at this and say, I remember that if we were to split this up as dy plus, sorry, let's rephrase this. So there's another way that people do this, and that's dividing everything by big P. And that leaves us with y prime is equal to lowercase, no, not equal. I'm okay. Plus lowercase p of x times y is equal to q of x, lowercase q of x. So generally what people will do is say, okay, y prime was going to be our dy part. If we move q over, we end up with p of x minus q of x times y dx is equal to 0. So looking at what we just did, m is going to be 1, n is going to be p of x minus q of x times y. And again, how we check for exactness, it's going to be our m of x is going to be 0, and a y is going to be p of x minus q of x. This is not exact, so find a particular function, mu of x, that's going to work for all this. And in this particular case, we get mu of x is going to be equal to e to the integral of n sub y minus m sub x all over m, which is going to be equal to e to the integral of, this is p of x minus q of x. And it's divided by m, which is just 1. dx. Oh, I'm sorry. Wait, hang on. I did that wrong. I'm sorry. Back up just a minute here. Our y was not multiplied to everything. That was my problem. Y was just multiplied to P. There we go. Okay, and then that means that in n sub y, q of x is just going to be 0. The derivative of q of x with respect to y. It's going to be 0. So we just get p of x. That's it. There we go. So in general, this is going to work for all first order linear differential equations. Ordinary. Alrighty. So, does anyone have any questions at the moment? Gonna look at chat finally. Yep. Yep, the Q of X did not have that. Yep, ode to joy. Oh, hey, Megamorph. Apologies. Yeah, so there was... So this was ordered a bit differently. Normally, what happens in a differential equations class is that we start off with first-order linear differential equations and be like, hey, check this out, and say, like, some of these end up working by just looking at it and saying, hey, remember that this is a product rule for some other equation that we had. So if we took the derivative of a particular product, then it would create this thing. And then let's try to find the special case of it and do that. And then like 2 weeks later, you'd talk about exact equations. And I found them to be completely disconnected when I took it. And so I was like, you know what? I don't like it. So we started talking about exact equations way back here. We started talking about our separable differential equations that we were looking at before. And I might as well just run right into the wrap-up here. Stucky, did you have anything you wanted to share? Or promote?
No, I'm streaming at sporadic times. My channel's cool, but that's all I got.
So follow Stucky if you want to get their take on mathematics and teaching and learning and all sorts of cool stuff. So, all right. If you want, I can let you go and then just wrap up.
Okay, that works.
Yep. Sorry for running way over.
All right. Take care. See you around.
Yep. Thank you. Have a good night. Okay. So we're gonna wrap up and going over everything we did tonight. So we started looking at this and saying, what are separable differential equations? We said separable differential equations in general are going to be of this particular form, m of t dt plus n of x dx is equal to 0. Basically, it doesn't really matter how they look as long as your m and n functions are multiplicatively attached with all of their little pieces. If you have any pluses and minuses that have mixed x's and y's, we're going to be in trouble. You're not going to be able to separate them into pieces. So if all of their terms are multiplicative, then we're going to be able to split them up and say, I've got our dx stuff that can go with our x stuff, and we've got our y stuff, dy stuff that can go with our function of y stuff. Again, if they're mixed functions, you can split them up, and eventually it just becomes this thing all over again, right? It's just a different name for the functions instead. They'll all be functions of x and y explicitly, separately. Hence, separable. I then discussed with Zach and Stucky, what about if we tried to make this left-hand side like something you've seen before? Again, Zach said, hey, that looks like a product rule. And we were able to say, okay, if you had the derivative of, and this is a multivariate derivative, or as I write it, the generic derivative of x cubed times y squared, then this is exactly what we get, exactly what we had up in the original. And so we said the solution to this is going to be psi of xy is going to be the function that we just found, x cubed times y squared, is going to be equal to some constant c, because here we found that the derivative, right, the differential equation was equal to 0. So if we, like, took the integral of these things... Actually, I didn't actually write it, so you know what? At this stage, basically what we were looking at was we wanted to take the integral of the generic derivative of x cubed y squared with some generic differential is equal to, we wanted then the integral of 0. Right, so then this whole left side becomes psi, which is x cubed times y squared, and the derivative, or the integral of 0 is just c. It's a constant. Okay. So we said these are called exact equations. And what kind of properties do they have? Well, if psi is equal to some sort of constant and could be by itself be a multivariate function, then we had psi, taking the derivative of psi with respect to x gets us our m from before. And taking the derivative of psi with respect to y gets us our n from before. And if it's true that these are separable, then we can have psi sub x dx plus psi sub y dy equals 0. And Zach had said, well, that means that if we take the other derivative of those separate pieces, then we end up with psi sub xy is equal to psi sub yx, which is a known property from differential equations. From multivariate calculus. Right? Taking two partial derivatives in the opposite order doesn't change anything. You're going to get the exact same thing. And also, this means that m partial derivative with respect to y should be equal to n partial derivative with respect to x. Okay. Excellent, Star Egg. So from our previous thing, we said, well, that should be the same. So m was 3x squared y squared. Take the derivative with respect to y, partial derivative with respect to y. We get 6x squared y. Take the partial derivative of n with respect to x, and we get 6x squared y. So yeah, they're the exact same thing, which means that the equation that we started with is exact. So this thing right here, 3x squared y squared dx plus 2x cubed y dy is equal to 0 is an exact equation, which means that it does come from a single function psi, which we can then find. So again, m is going to be psi sub x, so take its integral with respect to x. N is psi sub y, so take its integral with respect to y. And then in doing both of those things, we get that x cubed y squared plus some function of y alone is going to be psi. And from the other perspective, x cubed y squared plus d of x, again a function of x alone, is going to be what we get from this perspective, from n dy. So in this particular case, the only way that c of y and d of x could be the exact same thing, the only way that these two equations could be the exact same thing, psi, is if c and d are the exact same thing, or at the very least, a constant. And we said, okay, we're just going to separate them by a constant, no worries there. This produced a map like this, which is similar to a topographical map. These lines individually are called nullclines, which tell us basically what altitude are we at. It's the same thing. We then tried out a couple over here, and we said that 6xy plus 3 plus 3x squared minus 7 y prime is equal to 0. We found out, yes, these are exact this is an exact equation by taking their partial derivatives respectively, and then backing it up, taking its integral in the appropriate locations, ends up getting us 3x squared y plus 3x plus c of y, and that has to be the same as 3x squared y minus 7y plus d of x. In order to set, or when we set them equal to each other, we get that c of y has to be negative 7y, and d of x has to be 3x. It's the only way that this is going to work. And so c of xy is going to be 3x squared y plus 3x minus 7y equals c, our constant. Again, same deal here, but now we're dealing with sines and cosines. It was exact, and so we could follow the exact same prescription here, work its way back, find the answer. Again, c of xy is going to be y cosine x minus cosine x plus, minus 2 sine of x equals c, k, some constant. All right, that's when we got to this one, megalomorph. This is the one you were talking about. So, y plus, parentheses, 2x minus y e to the y times y prime is equal to 0. We, again, check that this is exact. So take m, take its partial derivative with respect to y, it's 1. Take n, take its partial derivative with respect to x, it's 2. Those are not the same thing. They're really close to each other, but they're not exact. So what do? Well, we said, let there exist some function mu. And first what we did is I said, let's just make it as a multivariate function of x, y. And we went through the whole process and said, well, if we try to solve for mu based on this stuff, it might be harder than the original differential equation we were trying to solve in the first place. So that's not really helpful. But we're allowed to say, let's have it just be on one variable. So we can choose, do we want it as a function of x, or do we want it as a function of y? And again, in general, we work down that if it's a function of x, we get this e to the integral of m sub y minus n sub x all over n over, times dx. Or if we want it as a function of y, it's going to be e to the integral of n sub x minus m sub y over m dy. In this particular case, the ones that we did, we would get that mu as a function of x alone is this nasty stuff. And you'll notice that it isn't a function of x alone. That should be ringing alarm bells. I should have thought of that at the time. Right, so since it's not a function of x alone, right, we could pretty much just rule this out and say, no, that's not going to happen. When we go over here, we said, okay, if it's a function of y alone, we end up getting 2 minus 1 over y. I like it. Right? We end up with this factor here, which is going to be y. We then multiply it to all terms. We get this stuff, which is this stuff. Is it exact? Yes, it is. We just get 2y when we take the appropriate derivatives. And then when we take the integrals in the appropriate locations, here we had a integration by parts, but we did that twice. We end up with this stuff. And over here, we end up with xy squared plus f of y. And again, xy squared with all this other stuff plus g of x. There's nothing with just x alone by itself, so g of x is going to be 0. F of y is going to be all that stuff over there. So then c is going to be xy squared minus y squared e to the y plus 2y e to the y minus 2e to the y is equal to c. That's what we get there. So then the question is, well, does that always work? And so I said, let us have a stand-in here. P of x times y prime plus q of x times y equals r of x, which is all ordinary first-order linear differential equations. This is a stand-in for that. It's generic. So if we do this, we can find that here, right, we could divide by big P of x, end up with just y prime plus p of lowercase p of x times y is equal to lowercase q of x. This is the way to simplify it. Which then gets us all this stuff here, right? We can separate, get our dx given to all the pieces. So dy plus p of x times y minus q of x times dx is equal to 0. If we try to take the derivatives in the appropriate locations, then we find that this is not an exact function, or this is not an exact equation, so we have to find mu. Let it be mu of x. And what we get here is, well, m was 1, so that's real nice. It drops out the denominator, and we just get n sub y minus m sub x. N sub y is just p of x. M sub x is 0. So it's just e raised to the integral of p of x dx is our mu, and that's it. Nothing else. Posture check, thank you. Hey Waffle, how's it going? Okay, and then if we want to do one last one for anybody who doubts the veracity of my claims here, y prime plus 3x squared y is equal to 5 tangent of x. Right, let's make this hopefully nice and easy. Is it going to be exact? Right, we could pull this over to the other side. We could do our usual thing. So this is going to be, again, y prime plus 3x squared y minus 5 tangent of x is equal to 0. And again, our dx can come across. Come on. Plus dy is equal to 0. Again, m is 1. M sub x, the thing that hasn't been done yet, is 0. N is going to be all that stuff. Again, equals 3x squared y minus 5 tangent x. And n sub y is going to be 3x squared. So, no, it's not exact, but mu of x is going to be equal to e to the integral of n sub y, 3x squared, minus m sub x is 0, divided by m is 1 dx. All right, if you want to do this shorthand, feel free. E to the integral of 3x squared dx. That's super nice. Mu is going to be equal to e to the x cubed. All right, now here's the other thing. You don't need to put a plus c here because that's going to drop a constant in front, and it's going to be given to all terms. So we can just divide by that again. Ta-da! So what does that mean? Okay, we're going to multiply mu all the way across, is mu y prime plus 3x squared y mu. And I'm going to return back to having the tangent on the other side is equal to 5 tangent of x e to the x cubed. Did I abandon that? Yeah, I did. That's fine. Well, yeah, that's mu also. Right, so this is going to be y prime times e to the x cubed plus 3x squared y e to the x cubed is equal to 5 tangent of x times e to the x cubed. Take the integral of all the pieces. And dx on both sides. Right, this whole thing is just the integral of the derivative of, parentheses, y e to the x cubed. Well, wouldn't you know? And this thing is the integral of 5 times the tangent of x times e to the x cubed, because goodness knows I don't know what that actually is. Alright, Wolfram people. Over here, right, this is a fundamental theorem of calculus. So this is going to be y times e to the x cubed is equal to that nasty integral. And therefore, y is equal to e to the negative x cubed times the integral that is above. 5 tangent of x times e to the x cubed dx. And again, you would normally solve this, but I picked a particularly nasty bit over on the right-hand side that it's going to end up being this tangent times e, so, like, gross. Thank you, Anders. Alright, so this is going to wrap things up for tonight. Apologies for running late. It's probably just going to be a thing. But I will release all of my guests, hopefully prior to half hour past when I'm saying that I am going to leave. Yes, and thank you, Zach, for coming. One more time, just for everybody. We have Zach, e to the 2i pi. We have Ian Stookie, who were our guests for today. If anyone is interested in becoming a guest and hanging out and having discussions about differential equations, particularly if there are other people involved, let me know. Come in on Discord and we'll talk about it. If there is like only a day or two that you want to come in and do that, that's fine. If you just want to like come in for a particular topic, I can do that as well. Whether you think like, hey, I'm an expert on this, or I really need to learn this, or whatever. If you are somebody who is known to the community, we can get you in and have you be part of the chatting group. And, oh, yes, Penn Center. I mean, Megalomorph, come on, right? Yes, Anders, yes, we will check homework. I just want to make sure we release everybody. Here is Penn Center's Discord. This has two purposes, mainly one, this is going to be the main repository for this class, and two, also check out Penn Center because he will be hosting, he has been hosting, and will continue to host a complex analysis class. So complex variables, I believe, is the name of the actual class. And it's really cool stuff. I remember taking complex analysis back in my master's, and I absolutely loved every minute of it. We're currently on week 2, So, yeah. You were saying you were rubbish at ODEs, too. It's perfect. It's perfect, Superbrain. Same prof. Yeah, that actually doesn't surprise me, though. I had pedagogical problems with a lot of my professors at Hopkins, and you know, wonderful people, great mathematicians, not really teachers. We've talked about that before. We'll talk about it again. Strong condition that yields incredibly rigid functions where magic can happen. Nice. Okay, Anders, yes. So let's go through homework. So the homework from last night. If anyone is interested, feel free and stick around. If you want to just lurk, that's fine too. If you want to just head off on your own, that's definitely fine too. I've been streaming for a while here, so I don't feel bad. So, right, trench homework. Of course, I didn't copy it, like, you know, onto its own thing. Okay. Page 61, examples 3 and 4. Apologies to everybody in dark mode. Okay, so 3 and 4 going across here. We wanted to look at existence and uniqueness of these particular things. Yeah. And let's also... Yep. Sorry. I'll move it over there. Scaladra. There we go. Okay. Right, try to find the area of existence. Initial value problem given here. A has a solution, so does it exist? Y prime is equal to the tangent of x, y. Yep, so first thing you were looking at was, let's make sure that... Yep, thank you, Femvox. Thanks, Phobos, Megalomorph, Superbrain, everybody for coming on in. Okay. So the basic idea is that we're looking for when is y prime going to be continuous. Ten out of 10. Yes, they do need to put in parentheses. Yeah. It's not particularly nice. Okay, so when is y prime going to be continuous? I need to plug my headset in before I just go completely out. There we go. Right. So there's a couple of different ways to do this. You can look at it and say, okay, this is going to cause problems, right? When x times y, the product, is going to be equal to any. It's not any multiple of pi over 2, it's going to be any odd multiple of pi over 2. So it's only going to be 2n minus 1 when n is an integer. And we can make it 2n plus 1 if you really want. It doesn't really matter, right? So, yeah, we're going to have problems any of these times here. Right, so you gave us nice dotted lines on a graph. Yep. Yep, okay. Yep, I like it. So we had what Andres did is to solve for n, well, sort of solve for n. To try to find, like, is there a particular set of integers for which this is going to not work, i.e., right, what are the, what's the full condition? So this is going to end up being, like you said, this is 2, come on now, 2 xy over pi is equal to 2n minus 1, add 1 to both sides, 2xy over pi plus 1 all over 2 is equal to our n here. Where n is any integer, right? This is where we have discontinuities. And so as you said, right, this is just going to be xy over pi plus a half is equal to some integer. So anytime xy over pi plus a half is or belongs to the set of integers, that's when we have problems. So you'd said, yes, make this so that it doesn't equal that. Yep. Right, so that's going to be the first thing to do, is to say, okay, given some particular x0, y0, we're going to plug those in. I mean, you did it so well. Okay, yep, thank you. There it is. Right, so the issue then becomes we want this to be as you wrote, you have some x0, y0 here, then we need to draw a rectangle which is going to contain this. So, right, like any rectangle that's like between here and here is going to work for us. So if it's going to contain that, yeah, if it's got to contain that, it looks like this, then in theory, right, we've got like this whole region where the particular solution can exist. If we will make it trippy, we go like this. Make it a 3D box. No, don't do that. Don't hurt people's brains. Fine. Right, so like the solution can exist anywhere in that box. And I say box. It's an irregular shape bounded by these particular things. If you really wanted to, you could find the box with greatest area. No, thank you. Not really. So, I mean, it basically says, like, come up with a rectangle in which this is going to be true. In theory, you could go kind of two ways with it and say, like, well, the solution is going to exist within, and then you kind of like pick a rectangle that's going to work. Or you say that the region that we're interested in is going to be a subset of this gigantic region here, some of which the solution does not exist in. Like, I don't like that, but all you're saying is that, you know, it is a rectangle in which there is a subset of numbers where you're going to get solutions. Like I said, I don't necessarily like just expanding the rectangle and being like, it's somewhere in this region. But it feels like it could, in theory, work. If anybody else wants to yell at me, that's fine too. Right, so part B says, what about uniqueness? I guess we could also, like, check and see if there's answers in the back. Look out! So 2.3, number 3, 71. Yeah, hell yeah, answers. 2.3, number 3. Right, so x0, y0 is not within that stuff where k is an integer. Yeah, so it was your first answer. Okay, so then what about tangent of xy for uniqueness? And in that case, so uniqueness is going to be a, same as above. So x0, y0 is not going to be... Nope. Right, is not going to be a... Was it odd multiple of pi over 2? I did -4. Let's be consistent, right? The least you can do, Obi, is be consistent. Where n is, again, some integer. Right? Cool? Yeah. Okay. And then we have to intersect this with... Nope. Union this with... the appropriate continuity domain for the partial derivative with respect to y of the function above. So f sub y like that is going to be equal to, here we have again f of xy, come on, is equal to the tangent of xy, x times y, that's different, which is going to be the tangent of xy, take its derivative as secant squared. Times the derivative of the inside with respect to y is just going to be x as a constant. So now we want to know, again, where does continuity break? And here, again, we have anywhere that xy is equal to, so in other words, xy cannot be equal to. Well, that's a cosine on the denominator, which is the same as tangent. So, oh, I'm sorry. I was saying you were right. So, good news. So yeah, I'd said like you might be able to expand this out and just say like, it's the larger rectangle. You can fit a rectangle. Like your guaranteed your guaranteed to exist solution must exist somewhere in this rectangle, which is true, but it doesn't exclude the corners, right? And then I looked it up in the book, and at the end of the book, it just says exactly what you said, the very first thing. x0, y0 is not this stuff, right? An odd multiple of pi over 2. That's it. And then for uniqueness, we said, well, you want the same continuity domain for f, and then also check f sub y, which over here we get, again, x times secant squared of xy. The domain problems exist at the exact same stuff that it does for tangent. So there's no change there. Do not exist when this stuff is equal to that. This one, and it's going to be integer. So that's what I wrote, right? That's what I wrote here, is like this union of all possible states in blue. I had said here, if we just do this out in the orange part and say like, close enough, in theory that could work. I'm not sure I necessarily like it 100%, but you know what? I think it's close enough. But again, they're doing this implicitly, where they're just saying x0, y0 can't be, product of x0 and y0 cannot be an odd multiple of pi over 2, and that's it. They just leave it like that. And f sub y ends up being this, which ends up having the same domain restrictions. So, again, no real change here from f to f sub y. Second one, y prime is equal to x squared plus y squared all over ln xy without absolute value. So, right, the product of xy must be greater than 0. So it doesn't matter if they're individually positive or negative, but their product must be greater than 0, which means that they themselves must have the same sign and not be 0. Okay. So then that means that x0, y0 product must be greater than 0. Done. Again, that's what they say. If you want to go further, again, we could talk about what that might mean. Right, and I don't even know what these individually necessarily... Okay, yeah. It's going to block out the entire quadrants where they're opposite signs of each other. Quadrants 2 and 4, right. I remember. Yeah, I remember seeing that. Partial derivative with respect to y is going to be a little bit trickier. It's fine. So on the top, our x squared's gone, and y squared becomes 2y over natural log xy. They can't just be reciprocals of each other. True. Yep. Right. X0 times y0. Wait. Oh, denominator not being 0. Right. Yes. And so this is intersect with natural log xy cannot be 0, which again, thank you, means that, yeah, x0, y0 cannot be 1. And x0, y0 must be greater than 0. Taken together, we can do two different things. And this is how it's written in exponential functions when we're doing that in pre-calc, by the way, right? x0, y0 is going to be equal to or belong to probably should be belong to. Okay, somewhere between 0 not inclusive and 1 not inclusive, union 1 to infinity. Okay, So we take the derivative with respect to with respect to y on top, and we just get 2y. And then plus, take the derivative with respect to, right, it's going to be a negative x squared plus y squared. Okay, and this is going to be the natural log of xy. That whole thing is going to be raised to the negative second power. And then we're going to take the derivative of the inside. So now this is going to be 1 over xy multiplied by the derivative of xy with respect to y only is going to just be x. Okay, that wasn't as bad as I was worried. Oh no. Is it different than this? Oh, yeah, you just brought them together. That's fine. Yep. So if you bring them together, we get a denominator that needs a y and a natural log of xy. On top in the first term, that's missing a y and also another natural log of xy, so 2y squared natural log xy minus parentheses x squared plus y squared. And then that has both the y and 2 natural logs at the bottom. So that one's good. We don't need to do anything. Oh, right, squared. Yep, so these are the same thing. And again, same deal. No, never mind. That was fine. So we have the same answer in terms of, right, with this, x0, y0 must be between 0, 1 and union 1 to infinity. And then, do we need anything else to intersect it with? So, I don't think we do. It's like the natural log itself can't be 0. But we know that. Our y's can't be 0. And our x's can't be 0. So that's out. I don't think there's any other restrictions. I think this is another case where we get the exact same thing in terms of existence and uniqueness. And I was saying this before. I don't think that I can remember seeing an example where the existence and uniqueness were actually different. There's got to be, right? Like somewhere. Has to be something that ends up like a different or extra term in the denominator. I guess, like, if it was an e function... Not really. I don't know. Maybe like an e to the negative x squared. When you knock that down as... Or e to the negative y squared. When you take the derivative with respect to y, and it's partial, of that thing, then you end up with... No. I'm trying to think of, like, any sort of... Yeah, I don't know. Trying to think of any sort of, like, random scenario. Might work, but... Coming up empty. Whatever. It's fine. Alright. Consider initial value problem. Y prime is equal to... 3x times y minus 1 to the 1/3, where y at x0 is equal to y0. At what point do we have existence or uniqueness for this stuff? Right. No, that's fine. So what do you think? Aha. Okay. I think we found one. I think that was intentional on my part. Yeah, so for existence, we're going to have that, in this case, it's just everywhere, right? So we don't have any particular restrictions on any part of this. That's not right. XY such that. No. What did you do? Part of R2, right? So we don't have any restrictions on any part of this in terms of X or Y. So we're good. In terms of uniqueness, now we've got to take our f sub y, which is going to be, here 3x is just the same, so whatever. yeah. So now we see it's root functions, right? Those with small exponential powers that make their exponent smaller than 1 are going to end up having something in the denominator afterward when they may not have had any issues beforehand. That's an easy one. Should have known. Right, y minus 1. This is going to be a negative 2/3 and multiply by 1/3 out front. So f sub y is equal to x times y minus 1 raised to the negative 2/3. Right? Or x over y minus 1 squared. Cube rooted. Alright, it's going to be... No, we don't need that. Okay. Yeah, so the issue here, there's only just the one. Y can't be 0. So for uniqueness, X can be all real numbers, and Y0 cannot be 0. Oh, yeah, 1. Jeez. The denominator can't be 0, therefore. Yeah, Y can't be 1. So up here, the only restriction is that Y0 cannot be 1. But otherwise, let's see, I think usually I end up writing this as x0, y0 belonging to real 2, except y equals 1. Y0. Right, that's the only problem that we're going to have. So we're not allowed to do that. All right. I mean, we might be able to find, what was it? P-plane 6, phase portraits. Boo. I wonder if this actually still works. Nope. Nope. So Rice was one of the places that P-plane just was always came from. Yeah, that's script. Really? Let me Google that for you. I mean, come on. Alright, fine. Click here, check out people in the D field. Yeah, it doesn't work anymore, does it? Yeah. So baseline plotter. Hey, here we go. That one's not gonna work. No, this is too much. D field. I need a direction field. GeoGebra. In theory. Yeah, that'll work. Okay, so this is going to be 3x times y minus 1 raised to the 1/3. Okay, so in this particular case, right, this would not be a unique solution at y equals 1, because if you select anywhere along y equals 1 as your initial condition, so, you know, 5, 1 or negative 500, 1, you will always get the exact same answer, which is the line y equals 1. Whereas if you select A, which is 2, negative 1, there's only one solution that you can get from it, and it's this one right here. It may be similar to B. Oh, you know what? No, it's here. It's that one. And B here is that one, I think. Yeah. So they cross at 0, 1. Or at least very, very, very close to it. Yeah, so the horizontal line y equals 1 is going to cause problems in that if you select anywhere along that line as your initial condition, you will always get that line as a solution. So these other ones are not horizontal. So there's a different part of differential equations that we're going to talk about later called stability. And there's actually a really good YouTube video. There we go. Yep, this is GeoGebra. So up and atom is a physicist named Jade, who is, or mathematician. I think technically she's a mathematician, but has been doing a little bit of work in physics and trying to understand the world just generally. But primarily, the question that she's working on here is the three-body problem, and she talks about the nature of stability. And so in it, I was actually going to bring it up for a completely different reason, but it was for the nonlinear dynamical systems and all that stuff that we were chatting about earlier. So yeah. Y equals 1 is an unstable solution, which is to say that if you start on y equals 1 anywhere for any x value, you will always stay there entirely. Right? If you are on y equals 1, you will always stay there forever. However, it's an extremely thin knife edge in that if you get slightly nudged to one side or the other at all, then your path will fall off of y equals 1 immediately and start increasing in speed faster and faster as it moves away. Yeah, well. So it's going to be an unstable solution because if you try to rest at y equals 1, you're going to find it's pretty much impossible. Right? It's like trying to balance a pen on your finger. It's a stable solution if you can hold it in that one exact spot, but it's extremely unlikely that you're actually going to be able to hold it in its perfect balance point like this. Unlikely, not 100% impossible, but Whereas if I hold something, hold a pen like this, this is in its natural state. This is a stable equilibrium point, a stable point. It stays down in this particular position, and if I move it away from it, it pretty much returns back to where it started in the first place, minus any random friction on my hand and all that stuff. So we have stable solutions where everything falls toward it if it's immediately disturbed from that equilibrium position. We have unstable where if it's disturbed from the equilibrium position, it'll never come back. And then we also have semi-stable, which are kind of interesting, where if it's coming at it from above, it's going to be stable and approach that particular position, but if it gets disturbed to the other side, then it's going to fall off. The example that she uses in her video is a saddle point. So you have something that's shaped, a single surface that is shaped like this, where if you go this way, it's going to be increasing in either direction, or stable, because if you disturb it, it's going to fall back to the bottom, or it's going to be this way going that way. So if you disturb it, it's going to fall away. Yes, so Lorentz attractors are going to be like the big one. A Lorentz attractor okay, more or less. Looks something like this. Oop, oh, I went the wrong way. Human error. Right, Lorentz attractors use very simple differential equations and end up having this chaotic particular behavior where they never return back to the same place exactly, and they like any sort of disruption in what has been created is not going to create the exact same thing ever again. And if you change its initial conditions, so like where it starts and all this stuff, then like overall its behavior is sort of similar, but at the same time, like its exact behavior is completely unpredictable. In fact, right, I have the equation for it here. Hang on. Somewhere. Chaos. Something that looks like this. Again, it's not exactly 100%, but whatever, it's close enough. You know what, that one's a different one. Hang on. Yes? Question mark? No. Well, that might be similar. Oh no, that's a Chen attractor. That's different. X prime is equal to 10 times y minus x. Y prime, it is x times 28 minus z minus y. Z prime is equal to xy minus 8z all over 3. So I'm not entirely sure if this is a true Lorentz attractor. I'm pretty sure it is. Yep, there it is. Yep, that's it. So if you were to plug these into a 3D model of a yes, so they're all functions of t. Yeah, they're all functions of t. Oh, you know what? I have that one actually here. Yeah. There we go. Hey. Good. This is the Differential Equations, Dynamical Systems, and Introduction to Chaos. Hirsch, Smale, and Divani. Pretty sure I used that for partial differential equations at some point, so... Oh, why thank you. It's more imprecise, which, I mean, probably gives it more sense of chaos than anything else. Honestly, this looks like a bundle of wires that you just kind of grabbed off the floor, so perfect, right? That is the ultimate in chaos. Okay. There we go. Right. For what points does that? Yeah, we already did that. Right. Cool. Goodness. Okay. I think that's going to about wrap it up. If anybody else has any other questions, let me know real quick here, and try to get them answered. But other than that, we'll be heading over to see if there's anyone still up doing mathematics. Otherwise, we will go see one of our other friends doing something real cool. Yep, Dr. Gold is doing SAT practice. Oh, yep, thanks. Oh no. Grog Mode is doing Returnal. I may have to pop in there as well, but probably send you all and go with you to see Dr. Gold, because his streams are always fun. Alright, yeah. We'll do Dr. Gold raid. Righto. So, I hope that I will see you all shortly. We're going to be back tomorrow night for just regular mathy questions type stuff. We're going to be back on Wednesday for class, and we're going to talk about slope fields. So we just saw what I was doing on the GeoGebra thing. We're going to basically like learn how to do them by hand and also be able to plot them on GeoGebra. I don't think I'm going to do it on MATLAB just because, but it's not too bad. I'll see if there's an easy way to do it on Desmos, see if somebody else has it, like, you know, did an applet or whatever. That's freely available. And we'll see how that is. Hey, Brandon. Oi. Just oi. Really hope it doesn't become a thing. In either sense, in any sense. I mean, yes, right? Like, so many other US presidents had attempts on them, but, like, come on. At any rate. Yeah, it's also becoming a thing globally. But also, if people stopped electing in people who claim themselves to be strongmen, then, you know. Had your own last year, cheese. Oy. Alright. We're sending it over to Dr. Gold. Like I said, I'll be back tomorrow for just mathy stuff, and then we'll be back on Wednesday for differential equations class again, and then we'll be back on Friday for gaming stuff, and who knows what else in the meantime. So, we'll see you all later, and I hope you have fun. My name is Obi-Wan Pez, this is N Simplex Pachinko, and we'll see you around. Have fun.